Okay, so at the end of the last video, we discussed if we could find a small measure for this tiny shift that's going to happen to our maxima. Our maxima is going to be shifted over very slightly towards the left when you're in the positive x on your graph of sine x over x, and towards the right for negative x values, so towards 0 either way. So I suggested that maybe there's a way of finding this value or finding an approximate solution to this value epsilon, and you could do that by substituting in 5 pi over 2 minus epsilon for your differential equation set equal to 0. So I differentiated sine x over x, and we found x cos x over minus sine x all over x squared. We set that equal to 0, so of course the denominator of that expression doesn't matter, the x squared on the bottom wouldn't matter. And then we substituted in x is equal to 5 pi over 2 minus epsilon. We're going to attempt to solve this now. So something that we can start by doing is writing down the addition formula rules. So that would be something that you could use in your interview, just to say something that is certainly true rather than leave a gaping silence. Something that you're going to use, something that would be useful in a situation, is much better than to just think about it in your head silently for ages. So at this point I might say, well, something we could use here is maybe the addition formula rules, okay? And I'd begin writing them down. If that wasn't the way to go about the problem, then your interviewer would likely say, maybe you can consider a different way of doing this problem, or here's another formula that you might use to solve this problem. And so they won't let you go down a rabbit hole into something ridiculous or something that's going to become impossible to solve or impossible to analyze. They'll instead guide you in a direction which is useful to them. Okay, so let's use the addition formula rules here. So we know that cosine A minus B, so I'm using the negative version because I have a negative sign inside my cosine here, is cos A cos B plus sine A sine B. And I can use that on this cosine 5 pi over 2 minus epsilon. So 5 pi over 2, cosine 5 pi over 2, is in fact 0 again. If we think about what cosine looks like, I could draw it on this curve here. I'll draw it in yellow. So it starts at 1, it crosses at pi over 2, comes up, and it crosses again at 3 pi over 2, and we know it's going to cross the axis again at 5 pi over 2, so it's 0. So that's very useful because it means that we can entirely ignore this first part, because whichever one you call A or B, so in this case our A is our 5 pi over 2 and our B is our epsilon, that means that our cos A is going to be 0, so we can ignore it. Sine A, or sine 5 pi over 2, is in fact 1, so we can ignore that as well. And we can actually just say that this is equivalent to sine of epsilon. So sine of epsilon, we're always going to approximate that to epsilon, okay, using the small angle approximation that I discussed a couple of videos earlier. Okay, so if I think about the other addition formula now for sine, I can use sine A minus B is going to be equal to sine 5 pi over 2, which I know now is 1, okay, multiplied by cosine epsilon, minus cosine of 5 pi over 2, and multiplied by sine of epsilon. Okay, so this is where A is 5 pi over 2 and B is epsilon. Okay, and again I can see a lot of this cancels out. So in fact here I know sine 5 pi over 2 is just 1, so I don't really need to write that down. And cos 5 pi over 2 is 0, so I can just cancel that all out, and this is just equal to cosine of epsilon. Okay, so this whole formula cancels down quite a bit. And at this stage, you might want to think, oh, do I want cosine of epsilon just to equal 1, or do I want cosine of epsilon to equal 1 minus epsilon squared over 2? Okay, and I can choose either of those. In fact, I'm going to choose one, and then I'm going to talk about what happens with the other one. So let's use cosine epsilon is just approximately equal to epsilon. Okay. Oh, sorry, is actually approximately equal to 1. I'm using the sine small angle approximation, yeah, when I should be using the cos small angle approximation. So if I use this on this formula, I can rewrite this. I can just say that that's going to be 5 pi over 2 minus epsilon, that's my x, multiplied by what I got from my cosine on my addition formula. So from my cosine on my addition formula, I got sine epsilon, which I'm approximating to epsilon. So I can put an epsilon in there, minus sine 5 pi over 2 minus epsilon. We found out what that approximates to. Well, it's just cosine epsilon, which we could say is epsilon. Which we can say is 1. Apologize. We can set that equal to 0. So when we set this equal to 0, we can now solve it. It's just an expression here for what epsilon is going to be. And because here we actually approximated cosine of epsilon to 1, okay, we said that's approximately 1. If epsilon is a small value, then that's a reasonable estimate to make. Then we should be ignoring terms of order epsilon squared. And you're going to get a term of order epsilon squared from multiplying these two brackets together, or multiplying 5 pi over 2 minus epsilon times epsilon. So that's going to give me a minus epsilon squared, and really I should be ignoring that, or saying that is shrinkingly small, because I've already said that terms of order epsilon squared are small. Otherwise I would have had to include an epsilon squared over 2 here. Okay, so we can do the alternative in a minute and see if we get a different solution, or see if our solutions can be set approximately equal to each other. They should sort of tend to each other as epsilon gets very small. So if we do that, we will get 5 pi over 2 multiplied by epsilon, and then we'll get a minus epsilon squared, which we're going to say is too small to consider, and we're going to get that minus 1 is equal to 0. Okay, so we can find that actually epsilon is approximately equal to, I guess I should be using approximately equal signs here, is approximately equal to 2 over 5 pi. Okay, which is quite small, it's 2 over 15. All right, so that's one way of finding epsilon, but what if we actually use the fact that cosine epsilon could be approximated to 1 minus epsilon squared? Well then, we're saying that actually this epsilon squared is not too small to consider, and in fact we could actually solve this. It's actually going to turn into a quadratic when we consider the epsilon squared values. So if we do that, we're still going to get 5 pi over 2 times epsilon from our first bracket, but we're also going to get a negative epsilon squared, and we're going to take away from that 1 minus epsilon squared over 2. Okay, and we're going to set that is going to be approximately equal to 0. All right, so when you do that, what do we get? Well, this 5 pi over 2 epsilon just remains the same. Then our epsilon times epsilon there, that's an epsilon squared, but we'll get another half epsilon squared from this bracket when we multiply that out. So when we do that, we're going to get 5 pi over 2 times epsilon minus epsilon squared over 2. So I've got an epsilon squared, a negative epsilon squared here, plus an epsilon squared over 2. That's going to equate to just half of an epsilon squared, and then minus 1. And we're going to say that's approximately equal to 0. So I'm going to just use equal signs from now onwards to solve for this epsilon. But remember, this is an approximate value because we've cut that Maclaurin series short. We've used the small angle approximation, which is only an approximation. Okay, but this is a quadratic, right? A lot of questions are going to end with a quadratic. Doesn't matter that we've got a 5 pi here, that's just a number. We can still solve it. If I actually multiply by -2, I can get my number, my equation a little bit simpler in epsilon. So if I do that, I will get just epsilon squared minus 5 pi times epsilon, and then multiplying by -2, that's going to be a +2 on the end, equals 0. Okay, so this is just a quadratic in epsilon. Usually there's an x here, and maybe that's a little bit unusual for some A-level students to be solving quadratics without an x in there, but it doesn't matter. You can have any number in there at all. We just use epsilon to mean a very small value that you can add on to something. So if I solve this using the quadratic formula, I will actually get 5 pi plus or minus the square root of 5 pi squared, all squared in fact, minus 4 times 2, so minus 8. Okay, all over 2. And it might be interesting to take the 5 pi out, okay, to take the 5 pi out, because what I might get you to do in a second is actually generalize this problem for any of the maxima or minima. Okay, so we're solving it for the 5 pi over 2 root. Okay, we're looking for the maxima near there, or actually we're looking for the small distance between the maxima of sine x and the maxima of sine x over x. But we could find the small distance between the maxima or minima of any of those points. So we could use 3 pi over 2 or 5 pi over 2 or 7 pi over 2 or something like that. So let's have a look at this. Let's take out the 5 pi from the bracket, and then you can actually put it on the outside. So we could call this 5 pi multiplied by 1 plus or minus the square root of 1 minus 8 over 5 pi squared. Okay, that's all under the square root, and all of this could be over 2, but maybe I'll just put the 2 on the outside. Okay, so this tells me a little bit more about the size of my epsilon here, and in fact I get 2 roots. So that's interesting. Why am I getting 2 roots from something that should really be only 1 root? We can look at the size of some of these numbers, the plus and the minus root. So if I think about the plus root in here, it's actually going to be a number quite close to 2, really. Okay, so I've got 1 plus the square root of 1 minus something quite small. So 5 pi is 15, 15 squared is 225, so 8 over 225 is quite a small number. So I can say that this square root is approximately equal to, well, it's near 1. Okay, it's a little bit less than 1. Okay, so one of our solutions is actually a number close to 5 pi. Okay, and that's quite weird. Why would I get 1 plus 1? It's a sort of a number quite close to 5 pi. And in fact, it's because we're actually finding the position of the other maxima, the maxima on the other side. So when we draw this, we've got one maxima here at around 5 pi over 2. But where is the maxima that is 5 pi away from that? Where is the epsilon? If epsilon was sort of 5 pi, if you're saying this thing in here is about 5 pi, you're actually calculating the location of the maxima over here at something close to minus 5 pi over 2. Okay, because the distance here is 5 pi, so that's where that positive root is coming from. We'd actually want to have a look at just the negative root. So just the negative root is in fact going to be 1 minus this square root of 1 minus 8 over 5 pi squared. And you could actually say, can I find an epsilon in general for any of these maxima and minima? Where are they going to be roughly? And in that case, all you need to do is say that my maxima and minima are close to n pi over 2, okay, for a general n, okay, where n has to be an odd number. If it's an even number, then you're at one of your roots of your equation, okay, where that's actually equal to 0. So when you put n into this formula, you're actually going to find generally that your roots are at, okay, if I take away from the square root here, 1 minus 8 over n pi squared on the bottom, okay? And that's what this small epsilon is. So it tells you this sort of deviation from the expected location of the root, like 3 pi over 2 or 5 pi over 2 or 7 pi over 2. So they might get you to argue here, does your maxima get closer or further away from these values of 5 pi over 2 or 7 pi over 2? If n gets bigger, does it get closer to n pi over 2 or further away to n pi over 2, these maxima and minima positions? And that's really like asking, do you expect epsilon to get smaller as n gets larger, or do you expect it to get bigger as n gets larger? So let's have a think about that one. So it's kind of a tough one to say, actually. N gets larger here, this number gets smaller, and you're having a 1 take away 1. That's going to sort of get closer and closer to 0 inside this bracket here. But n on the outside is going to get larger. So what we could do is then say, we could expand this and see if we can write this as a polynomial. We could actually, in fact, use the 1 plus x to the power of n formula that most people will know from A-level mathematics, that this is a binomial expansion, and it's an approximate value again. It's actually the same thing as the Maclaurin series for 1 plus x to the n. In this case, we could say our 1 is this one here, our x is this small value, minus 8 over n pi squared, and our n is actually going to be to the power of a half, because this is under a square root here. And most of you will know this formula to be 1 plus nx, and then it's going to be n times n minus 1 over 2 factorial, and then x squared, and it carries on. So you could do this expansion here because we know that we're looking for larger and larger n to see what happens, and you will find that you get epsilon is equal to n pi over 2, 1 minus, and then you're going to have 1 plus 1/2, okay? But your x is actually a negative number, minus 8 over n pi squared, and that's your x. Okay, so if you do that, you could say this actually carries on, but usually you only expand to the first position. If we look at what this is going to be, it's actually going to be, if you do the 1 minus here, this is just going to be a positive number here, and you're going to have an n pi squared on the bottom and an n pi on the top. So that n pi squared on the bottom is actually going to be mean that you have a 1 over n expression. So as you go to higher and higher maxima and minima, you expect this 1 over n. You expect, because epsilon is proportional to 1 over n, or inversely proportional to n, in fact, the higher this n is, the closer the maxima gets to 5 pi over 2, 3 pi over 2. Those odd half powers of pi. Half powers of pi? Half values of pi. Odd half values of pi. Okay, so that's something that we're going to look at in the future, how we can use the binomial expansion, the 1 plus nx binomial expansion, to solve a lot of problems in physics, as well as in graph drawing and thinking about where these roots are and where these maxima and minima are on these graphs. But this is a very good example of how you could show that. You could also reason it by thinking about this 1 over x. The 1 over x actually gets smaller and smaller and smaller as x gets bigger and bigger. And the gradient of 1 over x gets closer and closer to 0. So in fact, as we reasoned in an earlier video, it's the fact that this gradient is non-zero at sort of 5 pi over 2. The gradient of our 1 over x is non-zero at 5 pi over 2. That means that the maxima is kind of shifted over towards 0. If, in fact, that gradient gets closer and closer to 0, you can expect your maxima to get closer and closer to 5 pi over 2, because then it's not such a big deal, or it's not such a doesn't have such a large effect for it, the 1 over x being slightly larger when x is slightly less than 5 pi over 2. So this maxima will still be on the left of 5 pi over 2, but we know that the 7 pi over 2 root, the maxima is going to be closer to 7 pi over 2 than it was for 5 pi over 2. Okay, well, that's an interesting question. If you reasoned it this way, then that's a very smart thing to do. Perhaps reasoning it with the graph would be a little bit easier. They would lead you in this direction if they wanted you to actually do a binomial expansion. I was actually asked to do a binomial expansion in my Oxford interview, and maybe I'll give you that question in a later video. Thanks very much.